Welcome APK 5127. My name is Farid, and today I will be talking to you about heart rate variability. The great thing about this video is that you don't get to see my face. Why do you ask? Well, it's because I look something like this. Now, the real reason why you're not going to see my face is simply because all the analysis that we're doing today is based on software. And so I'm going to take you through that software and explain to you how it works and how that theory links to the physiological processes that I'll be talking about. Before we actually get started analyzing data and talking about what heart rate variability is, I just want to make a few things clear just for the sake of your understanding. When I talk about heart rate variability, I may throw around terms like RR interval, RRI, RSA, or HRV. HRV stands for heart rate variability. The RR interval signifies the time interval between two successive R waves on an ECG. RRI is simply the abbreviation of that, and RSA stands for respiratory sinus arrhythmia, which is the phenomenon of a variable heart rate based on your respiration. If any of you have taken heart rate, which you have, you've noticed that it speeds up upon inspiration and slows down on expiration. So for the sake of clarity, I'm going to restrict myself to using HRV when I want to say heart rate variability and RRI when I want to talk about the interval or the time space between successive R waves. Final note, this is not a discussion about heart rate. When we talk about heart rate, we talk about beats per minute and we talk about the number of beats. But a discussion of heart rate variability has to do with the distance between beats. So while you may have 1,000 beats per minute, we're not sure how they're spaced, if they're evenly spaced, or if they're bucking up and down in some crazy trend. And that's the whole point of this, is to really break it down and go beyond heart rate and see what's going on with the autonomic control of that rhythm. To be absolutely sure, I just want to give a quick visual illustration of what heart rate variability is. So as you can see, we've got a typical ECG waveform here, and on the left, or let's say close to the middle, you have a relatively large RR interval, highlighted by the green arrow. Two heartbeats over to the right, you've got one that's relatively small, and you see that pattern pretty much throughout the entire ECG. That's what we're looking at, is how does it change beat to beat? How much is it changing beat to beat? And when does it stop changing? So why are we looking at heart rate variability? Why are we looking at the distance between RR intervals? Well, the reason is because the heart, among other things, is mainly controlled by the vagal nerve, which is part of the parasympathetic autonomic nervous system. It's also controlled by the sympathetic nervous system, and it's the interplay between these two systems that controls your heart rate at rest and during activity. At rest, it's primarily controlled by parasympathetic activity, and during more stressful activities, even so much as increasing your posture, your sympathetic system kicks in a little bit in a reciprocal fashion to up the heart rate to accommodate whatever needs there are. The interesting thing we found is that in overtrained athletes, the sympathetic system takes over, and what happens is your heart rate is chronically higher. What's more, the variability between beats that we see, as I showed you on this ECG recording, disappears. It becomes more constant. So somebody with a greater heart rate variability is, first of all, more well rested, and second of all, more at rest in the moment. So it becomes a very good tool for being able to tell whether somebody is training in the moment or whether they're at rest but having been overtrained. So why do we use the R wave as our marker? Well, if we were looking at heart rate itself and we really wanted to get down to the roots of it, we try to record the sinoatrial node, but that's virtually impossible. The great thing about a heartbeat and the ECG it generates is that every waveform or every part of an ECG wave is the same distance from the beginning relatively than any other wave, and it holds from beat to beat, as in the P wave always goes first, and then you get the QRS complex, and then after a period of time you get your T wave, and so on and so forth. And so we use the R wave as a proxy simply because the P waves and the T waves sometimes disappear or get muddled or for some reason or another are hitting. The R wave is the most prominent and the most visible, and so that's what we use to measure the distance between two beats. One of the most interesting things about HRV is that it's already being used in professional sports despite a serious lack of literature on the topic. Seattle FC, which is Seattle's professional soccer team, uses it before every practice. Barcelona FC, arguably one of the best football clubs in the world, uses it for Rafa Marquez, as you can see, Andres Iniesta, or arguably the greatest player of all time, Lionel Messi. Every day before practice has to go through an HRV test to make sure he's not overtrained. Just a quick reminder, this actually is an ECG lab activity, so you will need to set up electrodes, for example, the 12-lead system that we did a couple months ago. You'll collect your data depending on what you want to study. The samples I'll be showing you in about a minute or so are supine at rest and standing posture, and that's about it. But usually the athletes that I spoke about earlier use them full stride, running, sprinting, jogging, whatever. It really depends what it is you're looking at. For the take-home HRV analysis applications that you've got on your iPod now or on your iPhone that you can hook up to yourself, they usually examine you right after you wake up. For the purposes of this lab, we will be looking at supine rest and standing rest, and that's it. Okay, so the next part of the lab is going to be the actual analysis of the data that we're going to do. To do that, we're going to need to get a piece of software. It's called Kubios. So first you're going to open up a browser. It's very easy. Their URL doesn't work very well, so just head over to Google. Type in Kubios HRV. And the first link in the results page should be what it is we're looking for. Yep, right there, biosignal analysis. This is going to take you to their homepage. And what you're going to do is just click on the right hand side, download Kubios HRV, follow all the installation instructions, and you're set to go. What should appear is an icon with a little heart and an ECG waveform on it, so you're going to double click on that. And what's going to pop up is an empty window. Now, the great thing about Kubios is that it deals with data collected by other programs, and usually that data is in the format of a MATLAB file or an Excel file or text file. Now, Kubios takes care of all three of those kinds of files, and if not, you can usually change your collection software to record in something that's more compatible. You're going to go open, and usually you're going to go look for the file elsewhere, but this time, because we only have a demonstration file, go to the folder you installed Kubios in this case I put it in Program Files, look for Kubios HRV, and inside should be a folder called Sample Data. Double click it, and open up the file that has been placed there for us. Now the first thing we're going to get is this mess of data. We'll go through it piece by piece, but before we do that, I want to say a little thing about HRV analysis. The whole purpose of this lab was to examine how heart rate variability, HRV, is modified in overtraining. Problem is, we don't have data from overtrained athletes that we can break down and analyze ourselves. We just have tables in different studies. The good thing is that the HRV profile changes in overtraining the same way as it changes in increasing levels of physical activity. So what we can do is look at increased physical activity, see how the HRV changes, and sort of extrapolate over to overtrained subjects and expect to see the same changes in those subjects. One thing you need to be careful of, the set of data we have here, according to the software manual, is of a subject who was supine for the first, I'd say, 5 minutes, and then was standing for the second 5 minutes. So what we're going to do is we're going to analyze those two sections of data and compare them. So the first thing we're going to do is actually split up the data. What you have to do is actually go to the left and drag the box over so that we can isolate the data. Go to the left hand side, click Add, and click OK, and we're going to get another window that pops up. Notice how that just appeared right over the first one. You're going to drag it over to the left, and you can adjust the boundaries of the areas you want to analyze. And as I adjust, you can see the bar graphs at the bottom changing shape based on the size of the data sample. And you can switch it and perform the analysis. Now, the reason we do this is because heart rate variability, which is the distance between every R wave, is subject to the heart rate. And heart rate is subject to all manner of things like posture and breathing rate and exercise rate. So you don't want to analyze two samples of data that come from two different types of activity, or else they're going to muddle your results. Another thing I want to show you is that if you in fact stretch this sample too far, you're going to take this huge dip and everything's going to change on your graphs and inside your data. You want to make sure you're well away from this transition period from supine to standing when you analyze your data, so that you don't get any artifacts from this switching here, this sort of like Valsalva maneuver that may have gone on as the person sat up. Okay, after we've added a second sample that we can click and drag, if we look at the top left-hand side of this window, what we're going to see is a bunch of, let's say, file data, or how we want to analyze this data. This is where we got our other sample for analysis that we could toggle between. But you also have this thing called artifact correction. Now, what artifact correction does is sort of remove some of the stuff that happens during data collection or sampling problems, stuff like that. The problem is that there are rules for how to apply this and tests to know how much of a correction you want to do. For the sake of analysis, I'm just going to go ahead and leave it at unfiltered. And the reason is simply because we don't know the rules that we have to follow to be able to do a proper filtration process. It doesn't change too much for the basic analysis that we're going to do today. Before we go on to the time domain analysis, I just want to point out this graph is in fact RR intervals, so the temporal distance or the time between any subsequent R waves, and is not in fact a graph of the heart rate itself. We're talking about variability, so we want to talk about the different distances between adjacent R waves. The first kind of analysis we're going to do is time domain analysis. Now, what does that let us do? It lets us study the temporal features of any different HRV wave, or RR interval, mean RR interval. Now, what does this tell us? Well, if you think about 60 seconds, which is generally how we measure heart rate in beats per minute, if you have a larger RR interval or larger average RR interval, you can presumably fit less of those within a 60-second time span. If your mean RR or average RR is less, you can fit more of them in a 60-second interval. Therefore, a greater average RR interval means a lower heart rate, and a lower average RR interval means a higher heart rate. And we can look at the data here. If you click on the first box and you look at the first average RR, we see it's at about 1.2 seconds or 1200 milliseconds, and that corresponds to a heart rate of about 49 or 50. If we click on the second sample, which as you recall is no longer in the supine position but standing up, the heart rate presumably went up to 65, and that means that the average interval between any R wave is now under a second, or about 925 milliseconds. The problem is that this is an average. It smooths everything out, and it doesn't give you any details about how this waveform changes over time. So it doesn't really talk to us about variability, but it does tell us what part of the graph we're situated in. To talk about variability, we want to look at something else called the standard deviation of RR intervals, or the standard RRI. If you look on the bottom here in the middle, we have a graph of the standard deviation of RR intervals. Now, if this plot or this normal curve was narrow, meaning all these bars were centered around the 0.9 second, then that means that there wouldn't be much difference from one RR interval to the next. They would all be around 0.9, and therefore your standard deviation would be small. But if you get a distribution such as this, which is more spread out, you can see that any given RR interval is probably different from another one. So the greater the spread of this curve, the greater the difference between any two RR intervals, which means the greater the variability. Therefore, a greater standard deviation of the RR frequency plot is a greater heart rate variability. And we can look at this and look at the first plot. The first plot has a standard deviation of about 69. The second plot has a standard deviation about 63. Now I know the second plot looks a lot wider, but it's because they changed the scale of the graph. You notice the first one goes from 0.9 to 1.4, and the second one goes from 0.8 to 1.05. So, greater heart rate variability comes from greater parasympathetic tone, and lower heart rate variability comes from greater sympathetic tone. So, this can be seen again in the standard deviation of the RR intervals. The first one has a standard deviation of 69 milliseconds, while the second one has a smaller standard deviation of 63 milliseconds. Lower HRV, it points to greater sympathetic tone. The problem is that we don't have any statistical tests right now to test between these, so we need a deeper level of understanding, a clearer picture, a more fine-grained analysis of what's going on. So the next measure that we're going to use is, if you jump all the way to the last row, called PNN50. What the PNN50 measures is how many of the total RR intervals you measured in any given sequence are greater than 50 milliseconds away from the one before it. So for example, if I had one RR interval that was, let's say, 1 second, is the next one 1050 milliseconds or greater or less than that? So this is measuring the percentage of RR intervals that are greater than 50 milliseconds away from their adjacent ones. Understandably, if you have more RR intervals that are less than 50 milliseconds away, that's less variable than RR intervals that are more than 50 milliseconds away. So if we look at the left-hand plot, again, this is the supine session, we see that 44% of RR intervals were more than 50 milliseconds different than their neighbors. If we go over to the standing activity, we see that only 4.3% of RR intervals were more than 50 milliseconds different than their adjacent ones. So what does this mean? This means that in the standing position, only 4.3% of RR intervals differed from their neighbors more than 50 milliseconds. So again, this is a measure of variability. On the left, we have a lot of RR intervals that are changing by a greater amount than on the right-hand side. The only problem with the PNN50 is that it doesn't tell you how much. What if we had 1,000 RR intervals that differed by 500 milliseconds? This measure would not tell us about it. So while it does give us a certain threshold to see how much one sample changes versus another, it doesn't tell us exactly how it changes. So right now we've got two measures that are talking about variability, standard deviation and PNN50, but neither of them gives us an exact picture of whether it's sympathetic or parasympathetic and how much of each is going on. For that, we need frequency domain analysis. Before looking at the data that the heart rate variability software is generating for us, it'd be good to understand exactly where frequency domain analysis is coming from and what it's doing. Most times, a wave that you see is not everything that you're getting, so to speak. Most waves in nature are composites of many other waves. For example, an oversimplified version is the black wave that you see on the screen in front of you. It oscillates with this odd bimodal pattern, and it's very difficult to tell what the frequency might be. What we do is we utilize a technique called power spectrum density, where we break down a wave into its component waves. All component waves are sub of the wave. Component waves simply add up at every point to make the resultant wave. So in this case, this valley right here on the black wave is the arithmetic sum of the valley on the blue wave and the valley on the red wave. If you have a point on a blue wave that is opposite in sign to the red wave, they subtract from one another. And the black wave is somewhere in between, as you can see. The special thing about power spectrum density is that the red wave and the blue wave are different frequencies. In nature, that usually means they come from different sources or have different influences. And the important thing is to see those different frequencies. And that's what the software is going to do for us. It's going to take our waveform from our RR intervals, and it's going to break it down and see what frequencies are hidden beneath the surface so that we can ascribe them to different physiological processes. Before we actually look at the values of the different waveforms, I want to pull your attention to the left-hand side. We're not going to change anything in this window, but just so you know, you can change the different intervals of frequency that you analyze. The only thing is we're going to leave them the same because the literature has looked at heart rate variability and has determined that these intervals are specific to different biological control systems. To be specific, HF is high frequency power and is from 0.15 Hz to 0.4 Hz. And that is significant because it reflects parasympathetic activity. On the other hand, LF, which is low frequency power, is from 0.04 Hz to 0.15 Hz, and that's thought to reflect both parasympathetic and sympathetic activity. We're going to leave VLF, which is very low frequency, band out of it simply because there's a lot of debate in the literature where it comes from, and there seems to be a high variability as to the source of this frequency between subjects, as in pathological subjects generate a VLF that's much different than healthy subjects. So for now, we're going to stick at LF and HF because they have been repeatedly shown to come from the same locations in terms of the autonomic nervous system. Now, if you look at these two graphs here, FFT spectrum and AR spectrum estimation, you can see that they change a lot as we click between our two samples. And the reason is because the frequency of each different waveform is much different. And this is why we split up samples, because we want to catch these differences between two different kinds of activity. But what's more important is the values right here in the power column. Okay? Now I'm going to direct your attention to the right-hand side simply because the AR spectrum estimation was pretty much developed as a more precise or an easier to interpret version than the FFT spectrum estimation. The reasons for this are way over my head. I don't understand. I'm just following the manual on this. And frankly, it doesn't really matter because what we're caring about right now is the numbers. Now we could look at the power. This is what they call the weight of a frequency. How much does it contribute to the overall waveform? As I showed you before with that graph with the black wave and the blue and the red wave contributed a certain amount of power and the blue wave contributed less power because its frequency was less. So we look here and we see the relative power of the high frequency, the power of the low frequency, and the power of the very low frequency. The problem is that if someone's heart rate is resting at a different level, these powers will be different. So what the software has done is normalize it to 100%. So we can see the ratio between each one so that we can compare it not only between subjects but between groups of people, and we can compare it within a subject. As we can see here, the high frequency takes up 6.4% of the wave power. Low frequency takes up 32.1%. And the very low frequency, well, we decide to ignore that for now. What's interesting is that if we change back to the supine, notice we were on the standing, if we change back to the supine, you go and you look and these numbers are vastly different. And you can tell just how different they are at looking to the ratio below them. As I said before, high frequency represents parasympathetic activity. Low frequency represents parasympathetic and sympathetic activity. So LF over HF essentially is going to be parasympathetic and sympathetic divided by parasympathetic. So what we're getting here essentially, according to the literature, is a ratio of sympathetic to parasympathetic activity. And when we look at the first one, we see a number that's about 0.5. When we look at the second one, we see a number that's 5.0, literally a tenfold difference. Remember, sympathetic influence is in the numerator, so that the number is getting bigger is signifying that the sympathetic influence is much higher in the second sample than it is in the first sample. This is expected, and you can see this in the AR spectrum graph right here. We know that high frequency is related to parasympathetic activity. When we switch to the second sample, that high frequency is basically gone, and we're reserved to low frequency here. We know high frequency has to do with parasympathetic activity, and so we see that parasympathetic activity almost disappearing totally when the subject stands up. And this is not surprising because we know with increasing levels of activity and increasing heart rate, those are due to decrease parasympathetic tone and increase sympathetic tone. So as we can see, the frequency domain analysis directly reveals the fact that the sympathetic system is taking over from the parasympathetic system. But what's interesting is that we can quantify it now with this ratio. We can see individual measures, but now we have a direct ratio of sympathetic to parasympathetic activity. The final type of analysis that you can do is a nonlinear kind of analysis. Now, there are many types of involved nonlinear analyses, but they are heavy on the mathematics and the statistics. So for the purposes of illustration, I'm only going to focus on the simplest one, and it's called a Poincaré plot. And on the bottom left here, you can see a Poincaré plot. Now, for the sake of comparing the two samples, which you can see are quite different, I'm going to pull up the overall report. And now how you do that, you go up to the top left, you get the report sheet, and you click on it. And what it's going to do is generate two different pages. Now what you want to do is put the one whose sample is highlighted on the right-hand side, and the one that's on the left-hand side. Now what that's going to allow us to do is compare the supine to the standing positions directly. Just want to adjust it for the sake of illustration here. Go to this one, do the same thing. Okay, so what is a Poincaré plot? A Poincaré plot is actually really simple. Every dot on the line is a combination of two RR intervals that are right next to each other. If you look at the x-axis, this is RRN. So this is any given RR interval plotted against RRN plus 1, which is the RR interval right next to it. So you take an RR interval, and its length of time is the x-axis. So let's take this outlier right here. The x-axis is about 1 second. So this represents one RR interval that was 1 second long, whose adjacent RR interval, or the one after it, at n plus 1, is about 0.9 seconds. And you do that for every single one, and therefore you get a very crowded plot. The interesting thing is that you can see the shapes of these two plots are much different. Now what this allows us to do is quantify in a different way the distribution. If you're to fit an ellipse with some sort of fitting program to it, you can see the shape of the ellipse that characterizes each of these plots is quite different. Now what does that tell us? I'll jump ahead to what the ellipse means, and then we'll come back and we'll break it down. SD1, which is the widthwise axis of the ellipse, represents short-term variability, while SD2 represents long-term variability. To understand long-term variability, I want you to think of a point along this line, let's say right here. Any point along this line represents two RR intervals that were identical. Notice how the x and the y coordinate are the same along this entire line. So if you vary along this line, the heart rate variability is not varying beat to beat, as this represents two beats that are almost identical in size. But if you take a cluster of RR intervals here and compare them to a cluster of RR intervals here, what likely happened is that you had a bunch of heart rates that were the same distance apart here, and then after a while they got shorter and rested over here, or they moved here. And this is why this is called long-term variability. Now if you look on this axis, I'll come back to this graph because it's easier to understand. If you take a point and you move it along this axis, for example, this outlier right here, what does this signify? This signifies that one RR interval was 0.9 seconds, while the other one was 1.4 seconds. So from beat to beat, the difference in RR intervals went from 0.9 to 1.4. This is why it's short-term variability, because this signifies the difference between adjacent RR intervals, while this axis signifies the difference between groups of RR intervals. And hence why SD2 is a signification of long-term variability, and SD1 is a signification of short-term variability. Understandably, it varies between physical activity conditions. With high heart rate variability, you have a greater SD1. With low heart rate variability, you have a greater SD2. And we can see this by quantifying the length of these axes. You look at the table on the left-hand side, and SD1 for the supine position is 47.6. SD2 is 84.3. If you move over, the SD1 of the standing position is 18.7, almost 3 times less, while the SD2 is only 87.1, which is still greater, but not by the same degree. So again, this is just another way to break down the analysis. So this might be the coolest part of the lab, is simply seeing, did everything we collect actually work? Does it mean anything? Well, you can't really take somebody's individual data and just say you are overtrained or you are not overtrained. It's more about collecting normative values, sort of like what height and what weight do you need to be at a certain age. There's no right or wrong answer, it's just where are most people. Here's one study that looked at 3 groups. One was a control group of sedentary, healthy individuals. The second was a group of trained, healthy individuals. And the third group was a group of trained but overtrained individuals. And so let's take a look at a few things and see what the specific difference is. On the left here I have the portion of the analysis we did based on the supine, because usually take-home heart rate variability analysis softwares are used right after somebody wakes up. So supine would be the closest thing to that. If we're going to look at time domain results, we can jump straight to the standard deviation. For supine we had 69 milliseconds. In our control group we have 44. In our trained group we have 104. And in our overtrained group we have 65. So while our mystery subject here is a little higher than the overtrained, he's way lower than healthy, but way above control. Remember, high standard deviation means high heart rate variability, which is a good thing, because that's what happens when you're well rested and healthy. So probably somewhere in the control to trained range. Again, doesn't tell us much. Let's look at PNN 50, 44.1%. For control subject, only 16.3%. For a trained subject, all the way up to 64.6%. And overtrained, 27%. Again, our subject had 44%, the overtrained down to 27%. Let's take another look, frequency domain analysis. Let's go over to the AR spectrum, and let's go straight to LF-HF total, which is about 0.456 for the supine position. If we look at our control, 0.47. Our trained was also 0.47. Our overtrained was 3.96, somewhat in the same range as our standing position for our mystery subject. So what does this tell you? This tells you if you get a normal subject and you stand them up straight, their heart rate characteristics are the same as an overtrained athlete lying down. So it just goes to show you how important it is to avoid overtraining at all costs and why this is becoming such an important science. If we're going to go look at Poincaré plots, the SD1, which was short-term variability, is 47.6. In our control, 29.5. In our trained, 75.2. And in our overtrained, 37.6. So again, we can see that in many instances, our control is a lot like our overtrained. If we go back up and we look at standard deviation, our overtrained was good in that it was better than the control, but not nearly as good as our trained subject. So you might be thinking, how do we distinguish between a control and an overtrained? But you don't need to. The whole point of HRV analysis is to compare to oneself. Athletes will take these measurements every day for days and days and weeks and months on end, and they'll build values similar to this column, the train status. And then every once in a while they'll wake up and they'll get values in this column, and this will tell them and their coach that they should not be training as hard, because if they do, they risk injury or just risk not training as much. So this is basically the initial analysis of heart rate variability. I hope you enjoyed it. It was a little involved, and I apologize I took more than the allotted 30 minutes, but I hope everybody learned something, and I can guarantee you within 5 years this will be mainstream athletic training equipment. Thank you.